This is just a quick spur of the moment hangout. I'm just kind of thinking out loud. I've been trying to, as you can see, draw some idea of the movement of the sun across the sky. And the drawing I have at the bottom is not, it's just an image I grabbed off of Google Images that shows a typical drawing of the solstices and the relation of the Earth to the sun in the standard model, and how it's tilted at 23.4 or 5. I think they got rid of the 4 because the opposite of 23.4 out of 90 degrees is 66.6. And well, we can't have that, so they made it 23.5. But anyway, it's speculation, but that's all I'm doing today. Anyway, taking the model as it is, because you have to find out what they're currently teaching to find out whether it works or not. Even, you know, if it doesn't work, then we have even better incentive and more people helping to figure things out, not by the current habit of scientism to refuse to falsify their theory, but to find what actually explains all the observed phenomena. And this drawing at the bottom of this picture is with the three, you know, with the Earth on each solstice and the sun in the middle, not to scale, of course. This is the way they think they explain the seasons and the movement of the sun. And the two tropics there, the North Tropic of Cancer, South Tropic of Capricorn, simply means, if you look at the definition, the point at which the sun is directly overhead, that is to say 90 degrees above you at its highest point during the day. That's all that means. Okay, so at the equinox, then the middle line, the equator there, the sun is at its highest point in the middle of the day on the, you know, the equinox. At the equator, it is 90 degrees straight up. It will rise directly east, set directly west, and in between times it will not veer to the north or south. It will stay 90 degrees, which is why you have issues with sundials. It would just be, in that case, I would think, a matter of shadow length rather than shadow direction, because there is no direction at the equinox at the equator. But as an experiment, you can prove that these lines make sense in that model, if that model is true, which is highly in question. At any rate, if you take a marker and you take a ball and angle it, you know, put it on a stick, so right through the center, so that it will turn on its axis, and put a marker to represent the sun at the site. Say that middle yellow ball there at the bottom is your marker, okay, representing the sun. If you point it toward the, say, the ball on the left, the Earth on the left, and just keep it level with that horizontal line there going across, or sorry, my marker, my cursor isn't looking at the right thing here. If you have your, say this is a marker with the tip right here representing the sun, and this ball, this polar axis line is a stick going through a ball, and you're going to spin it toward the right, basically, down toward the right, which is how the Earth supposedly moves, or spins on its axis at that angle. If you hold the marker right here and spin the ball, you will get this line. It will be straight, a straight line. Same with, you know, you could get 3 different colored pens, do the same thing, just to have them all evenly spaced and horizontal, and then have the ball at 23.5 degrees and spin it on its axis. You will get those lines, okay? And what that means is the extremities of the sun's path across the sky, where the sun at midday, at solar noon, which is its highest point, which is not related to the clock necessarily, that's the highest latitude north or the lowest latitude south that you will ever see the sun at 90 degrees. Now at the June solstice here in the Northern Hemisphere in the US, I verified by, I have a telescope with a good horizontal and vertical degree markings. And when I pointed it directly at the sun at solar noon, it was not 90 degrees. It was more like 70. And that makes sense. If you see this little calculation at the top, this is for my latitude. It seemed to me, I just kind of developed this formula just because it's probably already done, I'm sure, somewhere else. But I could figure out what degree this is going to be by taking 90 degrees, which is your y-axis, minus the difference between your latitude and this 23.5 angle. And the reason we can use that at the solstice, only at the solstice, is the June solstice, is because it will be at its most northern, far from the equator position. And so that calculation turns out to be about what I measured with my scope. So you can verify this with timeanddate.com. I know a lot of people don't like it, but so far, what I've checked personally, which is admittedly a small amount of data, it works out. I also verified this with sundials. We made some homemade sundials, and if you point them true north, you don't use magnetic north with a sundial, you use true north, which is Polaris. You set this out at what Time and Date calls solar noon, so that the shadow is pointing directly at the middle marking, the 12 o'clock marking. And then every 15 degrees of sun movement is half an hour, or an hour of sun movement, of the shadow movement, I should say. And it works out exactly the way you calculate it, whether you got a horizontal sundial. I have one horizontal and one more vertical, where the whole dial is angled at my latitude. And I have pictures of the two of them together, marking time exactly the same, and they both mark exactly as you find on timeanddate.com. Okay, now all of this so far, and for getting worried, is just that observations of the sun's apparent movement over the sky match timeanddate.com. The reason they match is up for dispute, but the fact that they match is not. I verified it at least for my location, my latitude, and when at the solstice, the June solstice, I noticed that two different analog compasses, one better than the other, but still, just to verify, the sun was rising a little bit north of east and setting a little bit north of west. Now, at first I thought, well, that shouldn't be possible. I'm way above the Tropic of Cancer. But since that tropic only means where the sun is 90 degrees, it does not mean where the sun rises in the east. It's always going to rise east no matter where you are, but how far north or south of east is the question. And you can see on my top diagram that I made, the red line is the equator. We're kind of looking at this angle from the northwest. And so there's the middle line is the equator, the path of the sun on the equator. It rises directly east, sets directly west, and goes 90 degrees when it's at its highest point. If you're in the north looking south, which is where I am, you see the sun is, say, close for the purpose of a thought experiment and reasonably close to observation. Sun directly rising east, directly setting west. This is a straight line parallel with this line. It's just a little shorter, but because it's farther north on this circle, the path of the sun goes to the south as it rises, and if it were 90 degrees, this line would be straight up. It's not 90 degrees. It's as if we've got a half dome here. We're at the flat bottom of an upside down bowl or something. This is the path of the sun. It will follow an arc on top of here and go south. It could still follow an arc and go straight up like it does at the equator, but when you're on, a parallel line to that center, it's shorter and the arc is going to be shorter, but this arc is not going straight up. It would be shorter if it was straight up. It's angled, it's tilted toward the south a little bit. Like I said, this is when the sun was at its highest point. I was measuring about 70 degrees at the solstice. And you would get the same thing at the opposite latitude south. You would probably see that same angle looking north. The sun would rise directly in your east, set directly west, and come up like at that same angle, at 70 degrees, which is 70 from the x-axis, so 20 degrees off vertical. And the question is, what does that mean? And I don't see how it works in the bottom standard model. I don't see how it works on any model right now, but maybe there's things I still haven't figured out that I don't understand about these movements. Because if you look, say you're at this point, it's nighttime, you know, the Earth is spinning like that, okay? It's going that way. And I'm in this northern hemisphere. Daytime is approaching, so the Earth is spinning like this. What would the sun look like in its motion from that perspective? Well, since I'm moving down toward the sun, since I feel stationary, the sun would appear to be moving up. That is to say, more north from me, from my perspective. But it does just the opposite. As I said, up here, it'll rise in the east, it'll go south, and it'll come back north again to set directly west. How is that possible in this model? Because if I'm turning this way, say the Earth is stationary and the sun is moving around it, as in standard geocentrism, the sun, in order to make this path, has to be looking as though it's coming south, not north. So I'm kind of stuck on that. Now I understand that this is a horizontal arc as well in relation to the sun, and would explain the fact that it's low in the east when it rises and low in the west when it sets. But it isn't just its height, it's its angle. There's two components here. Because if it was just a matter of how low it is, we would always have a 90-degree arc. But we don't. And if it's just that I'm this far from the equator, then why does it ever rise and set directly east-west? It should rise and set here. It should always do this red line, as far as I'm concerned. You know, and even at the equator, all three of these lines, if you bind all three of these arcs together and move them a little bit this way, a little bit that way, that's your two tropics, okay? Because even at the equator, the sun is not always exactly at 90 degrees. Because if you figure this with this little formula, if it works, if you are at 0 latitude at the equator and the sun is not offset, that is to say, there's no, for all practical purposes, that at the equinoxes, the tilt doesn't matter. So you will get no offset, so it's 90 degrees. In other words, 90 minus the difference between two equal numbers, two zeros, is going to be 90. At the solstice, now I haven't checked this, I hope somebody does, or maybe I will. At the solstice, at the equator, you should see the sun north of you a little bit. Maybe not, I don't know. But it's just, like I said, this is just stuff that's rolling through my head right now. And I'm just wondering, you know, if anybody has thoughts on that, because something doesn't add up. And like I said, if this movement of the ball Earth model is explaining why the sun comes up and goes down, then how does it explain that the sun directly sets east and west, but at its zenith, it's 20 degrees south at the solstice? I don't understand how this movement of the Earth explains observation. I don't understand that. So I don't know if anybody can help me figure that out. But now what if the Earth is flat? Okay. Then how do we still explain this stuff? Because at this, you know, when all three, like I said, if you grab all three of these and move them to summer solstice, you know, more north, then people in the south should see the sun on a flat Earth if it's going straight on the square Earth model or the whatever Pac-Man thing. The sun should always rise and set straight across at 90 degrees. Because they'll all tell you, well, it's not all of them, but some of them will tell you that the sun, there's one sun that it might move a little bit laterally, north and south, but you should not have this kind of a bend in the arc. It should always be, if it's going to rise north of you, say you're in the southern hemisphere, you're looking north at the equator, at the equinox, the sun is going to go up northeast, way northeast of you, set way northwest, and stay at that same angle from your viewpoint right here. Now, say you're at the Tropic of Capricorn down here, at the solstice, you should see the sun not only 90 degrees, but rising directly east or west. Now, if it's a circular path, the sun is going around here in a circle. I don't know what to do with this observation. You could say that this curve is the sun's path around, but then what do you do in the southern hemisphere? If the sun's always moving this way, then I don't see how in the southern hemisphere you would ever have this kind of an arc going toward the center like that. The sun would always, for everyone, do what it looks like it's doing here in the northern hemisphere. And another thing that Arwen brought out, a good point about perspective. If, say, for example, you're standing at a railroad track, a long, long railroad track, we're in the middle, and you see a train coming off in the distance, it appears to be moving slower the farthest you can see it. As it comes towards you, it seems to pick up speed. It's going really fast when it goes past you, and then it slows down again as it goes away from you. Sun doesn't do that. Even on the videos where I've seen where the sun is clearly coming toward the camera and then going away from the camera, the speed seems to be consistent. I don't know what to do with that. Now, let me stop sharing that for a minute and share a different window. Hopefully, I won't crash anything. Let me get my Excel spreadsheet of sunspots. Okay, I've been working on just watching this. I started the 7th of July, so it was a few weeks after the solstice, but that's where I marked my 70 degrees on the zenith, or the highest point of the sun, solar noon. And I described what the spots looked like and things like that, but I tried to also look at it as a clock face. Okay, so I could position the main spot or the main group of spots, and there's only ever been one cluster of spots since I've been watching, and several weeks in between when there weren't any spots at all, or I couldn't see the thing because of bad weather. But so if the clock face says 6, that's 6 o'clock by the hour hand, and percent from center, I would say, is about 3/4 of the way from the center to the edge. So you get what I'm doing there. And some of these I didn't write down at first. I was, just kind of filling in, making comments after I had put up a sun video. So eventually I started keeping better track. And I would show, for these color differences are for different days. So this was one day. I only looked at it twice, and it stayed about 6 o'clock and didn't move a whole lot laterally, I would say, from between the edge of the clock face and the center. The next day, it was at 3 p.m. local time, which, we're in daylight savings time or summertime. And so solar time, I think at that time might have been about, let's say, it's an hour and 42 minutes past clock time. So daylight savings time is 2 hours and 42 minutes past. But at any rate, this is just my local time, daylight savings time, okay, in the Eastern time zone. And I measured it at 3 and 7, and its only movement was it went from 2.8, meaning really close to 3 o'clock. And it seemed to go up to 1, but that's been about the only time, and these are my early measurements. I'm not real clear on whether I was using, my same conventions I'm using now. But anyway, since then, I've noticed that within a given day, it always moves clockwise. Every single time it moves clockwise. Okay. Now the lateral movement is unpredictable. Sometimes it'll stay in one spot for a couple of days as far as when I measured it. Sometimes it would move almost off the edge. In this case, it moved off the edge. I couldn't see it anymore for since the 17th of July till the 3rd of August. I did not see any sunspots. And then when they appeared again, there was one spot with another one next to it. It was very close to the edge. It was a little, like I would say 6:30 on the clock face. Then it moved up. Then it moved up, going on the second half of the clock face, between 6:30 and 10, or, going by the 12-hour clock, or just the numbers on the clock, and didn't move a lot laterally. Next day, it went from 7 to 8:30 to 10. It was a little bit closer toward the center, and so on. You can see I've been keeping these movements. A couple days ago, it was almost dead center. It was hard to figure which hour it was at because it was so near the center. Then, the best I could say it was that it was in the first quarter, like noon to 3, 12 to 3 on the clock. And again, it moved clockwise. And then I started to think, maybe it has this clockwise movement has more to do with my viewing angle than anything else, because as the sun goes across the sky, let me go back to my other drawing here. And I really didn't mean to close that. I just wanted to get the other screen share. We go back to this one and present. Okay, now say I'm standing here and I'm watching the sun and I take a reading at 8 in the morning, and each hour and I go up, I'm turning with the sun, okay? My angle to the sun is continually changing, and I'm wondering if that's why, since that movement is always clockwise, whether that's why the spots move clockwise. Maybe the spots don't really move around the clock face. They just, wherever they appear, they move in and out toward the center as they go along. So it could be either one. I'm not sure yet. I'm not sure whether it's, it would seem that the whole sun is moving. At first I was thinking, well, maybe just the spots move. We don't know if the sun is rotating at all. We can't tell. But it seems to me that if the spot movement, clockwise movement, is because of my viewing angle as the sun takes that arcing path, then it makes sense that if the sun is the whole sun is rotating rather than just the spots, then that would explain the spot movement. So let me look at the chat. I'm surprised anybody's here. Oh, I got a downvote already. That's good. Are we making fun of names? Let's not do that. Yeah, observation has to trump everything else. And that's what I'm trying to do here. I'm looking at my compass. I'm looking at my scope to get the vertical angle. And I'm marking the time. I'm marking sunspots. And I'm seeing this is how the sun moves. It can rise and set in a straight line parallel to the equator, yet at its zenith, it's 20 degrees south of that line. And presumably that would be true of any latitude, except the equator, where it will go straight up and down, and it makes sense. But these are a puzzle. But the problem is, if the sky is flat, then why do we observe arcing motion of not only the sun and moon, but also the stars? Everything in the sky arcs. And the question is why? Yeah, and so for, jet trails, they do, nobody disputes that that perspective will make it go closer to the horizon as it's farther from you. But here again, the problem is speed. The sun's speed is fairly consistent as far as I can tell. Maybe that's not true. I don't have a good way to measure that. And maybe, I'm sure other people do, but we need to know what the sun's speed is as it goes across, because that's a crucial element of perspective. Because if it's perspective, then the speed should increase as it gets nearer to you and decrease as it goes farther away. So yeah, we need to, I think we've been oversimplifying a lot of things. We need to take our observations and include in those timing and speed throughout the seasons, throughout the latitudes, and see what's going on, because you can't formulate your theory until you've collected your data, and you have to collect a lot of it from different places by people who are trustworthy. So back to chat, let's see. Railroad tracks with pure, yeah, they would, but would they have this angle of where the tracks are in reality straight? Say they're up, this is, we're down here looking up at the sky. Would they not only, if we were standing facing toward the tracks, say the blue line here is the tracks, and we're up here facing the tracks, and we hold out our arms, that's east and west, would the train's path or tracks appear to lean away from us as they came nearer? That's the question. So I'm just asking questions here, and things that we need to look for and get, like I said, speed, and take a whole bunch of things into account. Let's see. No evidence for curve in the sky. I'm not saying there's a curve in the sky. I'm saying there's a curve in the path of the heavenly bodies. Whether it's the same reason there's a curve in the path of a jet trail, I'm not sure. Because like I said, as the jet gets closer to you, it'll appear to be going faster. But we need to do more than perceive that its speed is one thing or the other. We need to measure it somehow. But like I said, we've got not only the jet trail rising and falling, we also would have to have it going at an arc this way. That is to say, that if I'm up here in the jets south of me, going straight across a flat sky, it's going to look like it's going up and then down, right? And here I am pointing at the wrong thing again with my cursor. Okay. Here's the actual path of the jet. I'm up here somewhere, and the jet will of course appear to rise and then fall as it comes near and goes away. But will it also appear to be south of me as well? That's a component I don't quite observe. I'm not sure. I need to observe more of it. But anyway, that's what I'd like to have clarified. And like I said, it doesn't necessarily have to be sky shape. It just is the path of the sun that I'm observing and wondering how many different ways it can be explained, especially as the sun, travels between the tropics. Like I said, if you grab these where these converge up here and move them this way and that way, what that would do to our observations. So anyway, okay, gravity, etc. It's just me talking. Anyway, just like I said, I was just thinking out loud. I drew this up today. I had seen other ones that I wasn't quite sure about. Let me show you. Let me get rid of mine. Let me see. Get rid of mine. Wake up there. This is a nice thing about having layers in a drawing. This is GIMP, not Inkscape today. I tried to make it composite of all the ones I saw, so let me break that down and get rid of the composite. Let me see. Here is one that they made, you know, they found in Google Images. Okay, this is standard model stuff where they will say the movements of the sun between the tropics, supposedly going in a straight line, but at 90 degrees. And then if you're other places along here, you're going to see this arc. Like this is the northern hemisphere. You would see that if the sun doesn't go any farther north than that, it doesn't go at 90 degrees, but you don't. If you're here, what you observe is this motion. You know, that the sun is going to go like this, not like that. Let me get rid of that one, put the other one. I have opacity changed here so I could overlay them all, but there's one, like here's the north and south. They had the red as the summer solstice in the north, that this is the path of the sun. This is from a person's perspective in the south looking at the summer solstice. And then the opposite way. Like here's the North Pole, you know, the Polaris. And when the June 21st came around, this is kind of what I saw, but this is directly east and west, and they're saying it goes like this, goes south of me, and then it comes back. Okay, so this is where I originally got all of these things. And I overlaid them at first and then said, that's really hard to look at, so I made that one. Anyway, that's what I was just doing a quick video about, was just to try to ponder some of these questions I have. What best explains all the components of this, the speed, the angle, if we have a straight line here, why, you know, in the northern hemisphere, if the sun sets or rises in the east, sets in the west directly, and yet when it's at its zenith, it's south of me. That's the kind of motion at the solstice that I'm wondering about. Of course, as the year gets later, you know, towards winter, this arc is going to be more of at an angle that way. But this is as far north as it's going to be where I am, because I'm not within the tropics. So the question is, this is the observation, what explains it? And I don't see how the I'm sorry, once again, I'm looking at the watch page and moving my cursor around instead of this one. So this was the, you know, the blue line is north looking south, and this is the most straight up that this arc is ever going to be where I live. Okay, it's going to lean that way toward the winter solstice and then come back up here. But it will never be 90 degrees. Only if you're within the tropics, especially at the equator. But any place in the tropics, you will at one time a year, you will get a 90-degree vertical sun at high noon, solar noon. So the question is why, and I don't see how that works in the standard ball model. I really don't, because like I said, if I'm here and the Earth is turning this way, that means I'm going down. And then I'm going to go back up again. That would account for the sun rising and setting, but it really doesn't deal with the component of the fact that at the solstice, the sun can rise and set directly east and west. It shouldn't be doing that at my latitude. I just, you know, maybe I just don't get it, but that's what's been puzzling me today. And I thought I'd just put that in a hangout and see what anybody thought, or maybe they want to work on it. and come up with a good explanation for all that stuff. So now let's see, chat mostly moved on to gravity. Yeah, that Cavendish experiment. Supposedly his motive for doing it was not to measure gravity at all. It was to determine the Earth's mass. But and I'd also read in standard documents that nobody has ever duplicated his experiment, and other people come and say, yeah, they did this at such and such university. Depends on who you want to believe, I guess. But the point is, the movements are so minuscule that there are so many other factors that could make the same result, such as electrostatic charge. And yes, you can have that with non-metallic objects, because with a certain strength of magnetic field, you can even levitate living things. We've all seen, there's a video of a frog being levitated by magnetic fields. So it can be done, and it doesn't have to be, excuse me, a metallic object to be levitated by magnetism. So anyway, whatever we want to call it, the downward force can be explained by electromagnetism, but the buoyancy density really does still beg the question as to why the direction is always toward Earth's surface. Because buoyancy and density are fine, but they're all being pulled in the same direction at different rates is the thing, and different intensities or whatever you want to call it, but they still have a direction, and the question is why the direction. Yeah, they use that to predict movements, but here again, it's a logical issue, because it's just like with the creation evolution debate that's raged for so many years, is we all have the same observations. The problem is interpreting them. And if you have two different models that can explain the results, then neither one is proved right. All you can ever do with a theory is falsify it, which is to say it can't work. And that hasn't been done with, to my satisfaction, evolution has been falsified a million times over. Of course, they don't agree, but now the question is falsifying the ball. And I think that given this illustration of why we have seasons in the ball model, I don't see how it explains the sun's motion. That's just my thing today. As for the neutral charge, I remember posting something on that. I think it was you or somebody else, Nick, in another chat another day. And I showed that you can't just go by individual atoms. You have to go by molecules. And the forces in an atom, whether or not they reduce down to zero, is irrelevant. When they clump together in a molecule, they often have a charge. So the charge is not neutral necessarily, because you're not working with individual atoms. You're working with molecules. The balls in the experiment were not neutral, and it depends on the experiment what materials they use, but you can have a net charge on a molecule. You often do. In fact, I think you almost always do. Like I said, with that frog levitation experiment, you put enough magnetic force on it and it will do strange things to the molecules, and they will have charges. So yeah, the thing is about magnetism is the amount of force is an issue, and we're all inside whatever force. We're trying to do experiments on gravity while we're in gravity, and that's going to skew the results. You would have to get away from whatever it is you're trying to isolate. And as far as I know, no lab on Earth is really isolating itself from gravity. You would have to have a zero-G gravity experiment done on Earth. And if you tell me it's been done in space, I won't believe you, because that's begging the question once again. So at any rate, but Nick, you're ignoring the fact that we have an actual experiment where a frog is levitated by magnetic fields. How is that possible according to your no charge theory? If it's negligible, how did it levitate? That's the question. And I don't remember where that link is. I'd have to go look for it. You can look for it. Look for levitating frog magnetic fields. You'll find it. and see their explanation. I know I had a good article I posted, I think it was for you the other time that this came up in a chat, and it showed that that there is enough force. If you put enough of a magnetic field on something, you will levitate it, even though it doesn't seem to normally have a net magnetic charge, and it won't be negligible anymore because it has to be enough to counter the force of gravity as popularly defined. So here again, it's the science stuff I got from a university that I looked up that contradicts what Nick is claiming about negligible forces. They can be overcome. So anyway, I just think this whole issue needs more development, more observation. We need to time everything. We need to have a lot of people observing, carefully measuring angles, directions, checking it against each other and different, like I said, people along one latitude would be a good experiment, and then compare that to other latitudes, different times of year, especially at the solstices and equinox, and then just see if we can duplicate these results in various models. And I really don't know about the square Pac-Man models, specifically the Pac-Man ones, because I think they don't account for these angles where the sun seems to dip toward the equator on its way across the sky. And one brief explanation supposedly had to do with distortion, but due to magnetic fields of the Earth. But here again, if you distort the light, you're also distorting the heat, and I don't know about that. So at any rate, Nick, are you denying that a frog has been levitated? Because it's been done. I've seen the pictures in a lab at a university. Somebody levitated a frog. How is that possible if what you're saying is true? Dude? Okay, I'm assuming you're being generic here. Like I would say you guys. I hope so. But I don't remember how strong the field was. It was fairly strong. But the thing is that we have that the argument that there is no magnetic net charge is false, because we can do this with frogs. We can make molecules that normally don't have a net magnetic charge or a net electrical charge have one by changing the magnetic environment. We can do that. That's how you counter gravity, okay? But it can be done on living things. That's my point, is it doesn't have to be metallic. It doesn't have to have a net charge in its natural state. Because if you can change that, you can make it anti-gravity. Oh, thanks, Jibby. Hey, Chow. Good to see all of you people here. Even the downvoters, at least they made a view on my video, which I haven't even done any Bible stuff, and I didn't plan to today. This was just pondering about the movement of the sun and sunspots. I didn't say it induced a current, Nick. I said it aligned the molecule's net electric charge so that it would counter gravitational force and make the thing anti-gravity. That's what I'm saying. You're not understanding what I'm saying. I'm not saying there was an electric flow of, electric current. I didn't say current. Current is a flow of electrons. I didn't say they were flowing. I just said whatever you think gravity is can be overcome with magnetism, even on things that are not metallic. That's my whole point. Anyway, I'm not pretending to be any scientist. I'm just saying when somebody says that that gravity can't be due to magnetism, and yet you can overcome it with magnetism on things that are not metallic, Houston, we have a problem. That's the point. Anyway, All I'm saying is that I'm observing the sun do certain things, and I'm trying to figure out why it does these certain things. I didn't even plan to talk about gravity today, but I never said gravity does not exist, Nick. Why did you even say that? Have you ever heard me say gravity does not exist? I've always said there's a downward force, whether it's neutral buoyancy density or standard gravity. The point is there's a downward force. So you can call it gravity if you want. I never said there's no such thing. Things fall. And when you have the buoyancy illustration of different density object, different things in a tube with, the heavier, denser things at the bottom, it still has a direction. I never denied that, and you can't find me ever saying otherwise. And gravity can be overcome with magnetism, and it does not require that you have flowing electricity. So, all right, well, you got to make things clear in the chat. When you're typing, nobody knows who you're talking to. Anyway, I never said that there's no such thing as a downward force. But I did say that there's such a thing as using magnetism to make even non-metallic, non-ferrite things levitate. Let's see. That's the question. What does give direction to anything? Why is it that any two masses should attract, even if they're not metallic, even if they don't have a magnetic field? What somebody the other day was saying, was it Venus or Mercury? One of those doesn't seem to have a magnetic field. And yet there it is being held in place by the sun's magnetic field, allegedly. How is that possible if it doesn't have a field of its own? That doesn't make sense. Anyway, I don't know curved water. Why does it have a direction even in the standard model? Why should masses attract? They don't all have magnetic fields. As I was just saying about it was either Venus or Mercury. No magnetic field detected, yet it acts like it has one as far as anybody can tell. It orbits the sun like anything else. And nobody has really proved that what they think it's made of. They assume in order to create magnetic fields in most space bodies that they must have a liquid ferrite core of some kind, that the movement causes a magnetic field. But they don't know that. Nobody's drilled deep enough to find out even on Earth. What is gravity? Why does mass attract to mass at the center? You can't explain it either. Oh, we got, you know what? I'm going to probably shut down anyway. I know that's what they want, but we don't need trolls messing with the chat. It's trolled enough already, but at least the other people weren't being vulgar about it. I'm just saying that there is a downward force. Neither model can explain it. Nobody can say, even in the Cavendish experiment, if it were true, why it is that one mass should attract another. Why does it work? You don't know. Nobody knows. So asking me the question, or asking any flat earther the question, makes no point whatsoever, because standard cosmology can't explain why there should be any attraction between masses. There's nothing in those two metallic balls that Cavendish allegedly had that created a magnetic field. Why should they move toward each other? If there was no magnetism involved, why should those two hanging magnetic balls move toward each other? There's no reason. They should always be pointing down toward the Earth, because the Earth's magnetic, or the Earth's whatever downward force, would overcome any negligible force in the individual items hanging from strings. They should not have moved toward each other at all. But you claim they did, and this proves gravity that moves downward, even though the balls allegedly moved horizontally. How that proves a downward force, I don't know. How do you know gravity is not magnetism? That's the point about the levitating frog. You can levitate things. You can overcome gravity with magnetism. So you can't say it isn't. At any rate, I didn't start this to talk about gravity, and I mostly just was saying, we need to work on this. Somebody explain this to me in a way that makes sense. And all the models, the one at the bottom from standard cosmology, does not explain what I'm seeing the sun do in the sky. That's all I'm saying. So anyway, I got other things to do. Thanks for coming. I'll see y'all later. So let me find that stop button. I know it's here somewhere. There we go.